This is continuation of video 2a, and in this video you will learn about the experiments that led to the discovery of subatomic particles. One of the postulates of Dalton's atomic theory is that the atoms are these hard spheres which are indivisible and indestructible. Now the next question was, what are these atoms made of? To answer this question, scientists in the year 1850s were working with electric discharge tubes called as cathode ray tubes. They took a long hollow tube and pumped out all the air out of it to create a vacuum. They fixed two metal plates at the opposite ends of this tube and connected these metal plates to an external power source. The negatively charged electrode is called cathode and the positively charged electrode is called anode. When they turned the power on, they saw a beam of light or radiation emit from the negative electrode and move towards the positive electrode. Since the radiation emanated from the negative electrode, that is cathode, these rays were called as cathode rays. To understand what this radiation is made up of, English scientist Thomson studied these cathode rays further. What he did is the following. He took two metal electrodes and put them perpendicular to the cathode rays. When he turned the power on, the cathode rays bent towards the anode, that is the positive electrode. Now, what do you think he inferred from this experiment? Since the cathode rays bent towards the positive electrode, he concluded that the cathode rays are made up of small negatively charged particles. He called these particles corpuscles. We now know that these particles are electrons. Since the discharge tube is evacuated, that is, there is nothing inside the tube, he reasoned that these negatively charged particles must have come from the metal plates. So, he repeated the experiment with different types of metal plates to verify if these negatively charged particles are characteristic of any particular metal. He found out that all the metals he used emanated these particles. Therefore, he concluded that these charged particles are fundamental to all the metals studied. That is, they are present in all the metals. In addition, he also measured the charge to mass ratio of these electrons. He found that value to be 1.758820 times 10 to the 8 coulombs per gram. Before the experiment, atoms were thought to be the smallest particles that can exist and that they are indestructible and indivisible. And the experiment proved that there are negatively charged particles inside the atom. That is, the first subatomic particles were discovered. In the next slide, we will study the implications of this discovery. Thomson then started thinking about the implications of his discovery. Atom is electrically neutral overall, and he just found out that there are negatively charged particles called electrons inside the atom. He reasoned that means there must be positively charged particles inside the atoms to balance the negatively charged electrons. Now the next question was, how are these electrons arranged inside the atom? Or what is the structure of the atom? He proposed that the negatively charged electrons are distributed randomly across a positive charged cloud. He got inspired by his favorite English dessert, plum pudding, in which the plums are randomly distributed in the dough. Therefore, this model is often referred as the plum pudding model of atom. If plum pudding is not your thing, you can imagine a chocolate chip muffin. In a similar way, the chocolate chips are distributed randomly in the dough. The next big experiment came from Robert Millikan. He performed a very famous experiment called as Millikan's oil drop experiment to calculate the charge of an electron. This is the cross-section of the experimental apparatus used by Robert Millikan. He sprayed some fine mist of oil into this chamber and allowed the droplets to fall down due to gravity. With a telescopic eye, he could monitor how fast the oil drops are falling. He then shot X-rays into the chamber. These X-rays ionize the air surrounding the oil droplets, that is, knock out an electron from the air particles. The electrons ejected from the air get stuck to the oil drops, making the oil drops negatively charged. What he did next is, he applied voltage to counteract the gravitational force on the droplets and kept them suspended. When these oil drops are suspended, that means the gravitational force pulling them down is exactly balanced by the electrostatic force pushing them up. He used the formulas that were known at that time and simple math to calculate the charges on these oil drops. The following is an example of a dataset that he got from his experiment. Charge on the oil drop 1 is 14 coulombs. Charge on the oil drop 2 is 35 coulombs. Charge on the oil drop 3 is 21 coulombs. What do you think he inferred from this data? He noticed that all these numbers are multiples of a very small number, which is 7 coulombs. That means this must be the smallest charge that can exist, which is the charge of the electron. And each of these oil drops must contain either one electron stuck to them, or 2 or 3, and so on. The charge of the electron that he calculated was within 1% of the modern day value of the charge of the electron that we use, which is 1.602 times 10 to the negative 19 coulombs. He also calculated the mass of an electron by using the electron charge that he calculated and charge to mass ratio that Thomson discovered. In 1911, Ernest Rutherford and his colleagues carried out an experiment to test the validity of Thomson's plum pudding model. That is, they wanted to check if it is a good representation of the structure of an atom. Around late 1800s, scientists discovered that certain unstable atoms spontaneously disintegrate into more stable ones, and in this process produce high energy radiation. They call this phenomenon radioactivity. One type of radiation emitted by these radioactive atoms are called alpha particles. These alpha particles carry a charge of 2+ and are approximately 7,000 times heavier than an electron. Now we know that these alpha particles are helium-2+ ions, that is, nuclei of helium. Ernest Rutherford and his colleagues decided to use these alpha particles to probe the structure of an atom. They took a very thin gold foil of few atoms thick and shot alpha particles into the metal foil. He thought that if Thomson's plum pudding model of the atom is in fact correct, then the massive alpha particles should go through the foil easily with very small deflections. He performed the experiment and found out that most of the particles passed through the foil as expected. To his surprise though, some of the alpha particles were deflected at very large angles, and even fewer particles were completely reflected. Ernest Rutherford and his colleagues were really surprised by these results. He wrote in his book the following quote: "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Since their experimental results disproved the previous model of atom, that is the plum pudding model, they decided to build a new model of atom based on their experiment results. Remember that the gold foil is super thin, that there are only a few atoms of gold in its thickness. As most of the alpha particles passed through the foil, they proposed that most of the space inside the atom is empty and is occupied by electrons. The second observation is, few alpha particles got deflected or reflected. He reasoned that for a massive positively charged alpha particle to be deflected and sometimes even reflected, it must hit something that is positively charged and much heavier than alpha particles themselves. Therefore, he proposed that all the positive charge and the mass of the atom is concentrated in a tiny region in the center of the atom. Rutherford called this nucleus. He named these positively charged particles as protons. Based on the ratio of alpha particles that got deflected or reflected to the particles that went through, he also calculated the size of nucleus relative to the atom. According to his calculations, the nucleus was approximately 10,000 times smaller than the atom. So, we now have the nuclear model of atom, where the mass and positive charge sits in the center of the atom inside the nucleus, and the electrons are randomly distributed outside the nucleus in the empty space. Scientists around the same time noticed that the mass of an atom was higher than that of all the protons and electrons combined. So they proposed the existence of a neutral particle which increases the mass of the atom. In 1932, James Chadwick discovered neutron, a neutral particle that is also present inside the nucleus. Let us summarize what we have learned so far. Protons and neutrons are present inside the nucleus, with electrons present outside. The number of protons and electrons in an atom are equal, thus making it electrically neutral. As you can see, the absolute charges of the proton and electron are same in magnitude but opposite in sign. That is, positive charge on the proton and negative charge on the electron. Since these are the smallest charges that are possible, and all the other charges will be multiples of this value, it will be easier to assign them a relative charge of 1 plus and 1 minus. Now let us look at the mass of subatomic particles. The mass of proton is 1.67 times 10 to the negative 24 grams, and the neutron's mass is very close to that. However, if you see the mass of electron, it is 9.1 times 10 to the negative 28 grams. This is approximately 2000 times smaller than that of the mass of proton or neutron. If we take around 2000 electrons and put them together, the mass of these 2000 electrons will add up to make mass of one proton or one neutron. So what we can say is, most of the mass of an atom comes from its proton and neutrons, and the electron mass is negligible. Mass of these subatomic particles can also be expressed in another unit called as AMU, which stands for atomic mass unit. We will discuss more about the AMU in the following videos.